At first there was a tiny ball of infinitely dense matter, then it all exploded, giving rise to the atoms, molecules, stars and galaxies we see today, or at least that's what physicists have been telling us for decades. However, recent theoretical research in physics has introduced a new perspective that suggests that the early universe might not be as early as previously thought. Instead, it could be part of a cyclical process in which the universe undergoes a series of bang-and-bounce cycles that have happened at least once and possibly in an infinite loop. Renowned physicist Brian Cox also challenges the Big Bang theory, stating that something cannot come from nothing. The James Webb Telescope has made a remarkable discovery that contradicts the notion that the Big Bang marked the beginning of the universe. This revelation raises the question: if the Big Bang was not the beginning of the cosmos, then what was? Scientists have a pretty good idea of the early universe we know and love, like the Big Bang theory. According to this model, the universe was much smaller, hotter, and denser a long time ago than it is today. In that ancient hell, 13.8 billion years ago, all the elements that make us up formed in the span of about 12 minutes. According to this theory, our entire universe, all the stars, galaxies, and everything else, was once the size of a peach and had a temperature of more than 1 quadrillion degrees. Surprisingly, this fantastic story is consistent with all current observations. Astronomers have studied everything from residual electromagnetic radiation from the early universe to the abundance of the lightest elements, and have found that it all fits with what the Big Bang predicts. As far as we can tell, this is an accurate representation of our early universe. Although the Big Bang theory is solid, we know that it is not complete. An important part is missing: the first moments of the universe. The challenge to understand it comes from our limited physical theories. We use relativity and particle physics, but when exploring the beginnings of the cosmos, the math gets too complicated and our current tools don't give clear answers. The existence of a singularity at the beginning of the Big Bang tells us that there are things unknown. This extremely dense point does not fit well. We need new physics to figure this out. Our current toolbox is not enough. We require a new physics, such as string theory, that addresses gravity and other forces at high energies. This theory says that it can explain the beginnings of the universe. Within string theory appears the idea of an equiradic universe, taking its name from the Greek term for fire. According to this, the Big Bang that we know of was the result of a previous event, indicating that it was not an absolute beginning, but part of a larger process. This notion is expanded in cyclical cosmology, a theory motivated by string theory. Although the idea of a universe in cycles has been debated for centuries, string theory gives it a mathematical basis. The cyclic universe oscillates between explosions and collapses in an infinite cycle, stretching into the past and into the future. Roger Penrose, laureate of the Nobel Prize in 2020, proposed this theory. He found a mathematical connection between the early universe of the Big Bang, characterized by extreme heat and density, and the future state, cold and without matter. His theory suggests that both states become identical in limits. Amazingly, the complete lack of matter could be the cause behind the creation of all matter in the universe. From this perspective, the Big Bang originates from a nearly imperceptible remnant left after all matter in the universe has been consumed by black holes, eventually evaporating into stray photons in a vast vacuum. In this way, the entire universe emerges from something that, from another point of view, is essentially as close to nothing as can be imagined. However, this nothing is still a form of something. It constitutes a physical universe, even if it is an empty one. The mystery lies in how this same state can be interpreted as both a cold and empty universe and a hot and dense universe, depending on the point of view. The key lies in a complex mathematical technique called conformal rescaling, which is a geometric transformation that alters the size of an object while preserving its shape. Penrose showed that the cold, empty state and the hot, dense state can be connected through such rescaling, aligning their spatio-temporal structures. Although their sizes differ, it is difficult to understand how two objects can be identical in this way despite having different sizes. However, Penrose argues that the concept of size loses its relevance in these extreme physical conditions. In conformal cyclical cosmology, the sequence of events unfolds from an old, cold state to a young, hot state. The presence of the hot and dense state is a result of the cold and empty state. But this causal relationship does not follow the usual pattern of cause and effect in terms of time. In these extreme states, both size and time lose their conventional meanings. The cold, empty state and the hot, dense state exist on separate timelines from the perspective of an observer within their own time frame. From this perspective, the cold and empty state would go on forever, while the hot and dense state that it originates would begin on a new timeline. It may be useful to see the hot, dense state as emerging from the cold, empty state in a non-causal way. These concepts have philosophical implications and have been explored by philosophers of science, especially in quantum gravity, where traditional ideas of cause and effect seem to change. When we reach the limits of our comprehension, physics and philosophy mix together, and it is difficult to separate them. Cyclic cosmology provides detailed but speculative explanations for the origin of the Big Bang. Even if Penrose's ideas are supported in the future, they might not answer the deeper philosophical question about the origin of physical reality. How did this whole system of cycles come about? This brings us to the question of why there is something rather than nothing, one of the essential philosophical questions. For our conversation, we will focus explanations in the realm of physics. There are three main possibilities about the origins of these cycles. First, there may be no physical explanation. Second, there could be an infinite series of repeating cycles, with each cycle being a different universe. The quantum initial state of each universe would be defined by something from the previous universe. Third, there is the option of a single cycle and a repeating universe, where the beginning of the cycle is explained by a characteristic of its own end. The last two options avoid uncaused events and provide a full explanation within physics. Penrose proposes an infinite cycle of events, influenced by quantum theory. In quantum mechanics, a system can be in many states until it is observed, at which time one is chosen at random. Penrose suggests that each cycle is influenced by random quantum events, creating differences between cycles. This interests experimental physicists, who can detect clues in the radiation from the Big Bang, observed by the Planck satellite. Penrose and his team think they have identified these clues, linking them to radiation from black holes in the earlier universe. However, other scientists dispute this, and the validity of their observations is uncertain. The James Webb Telescope has revealed things that defy cosmology and the Big Bang. They have found enormous ancient galaxies, unusual for their time. These galaxies existed when the universe was only 3% of its current age, much earlier than expected for their size. According to theories, the early universe should have small galaxies, not large ones. These galaxies raise questions about how they formed. According to previous ideas, the universe cooled after a rapid expansion, allowing gas to condense and form stars and galaxies in the Dark Ages. But the discovery of these huge galaxies suggests that the Dark Ages may have been more active than we thought. Dr. Emma Chapman, an astrophysicist at the University of Nottingham, mentioned that this implies that the universe experienced abundant star formation much earlier than expected. More in-depth observations and analysis will be needed to confirm these findings and understand what they mean for our ideas about the universe. The research team plans to use spectral images to accurately measure distances and estimate the masses of galaxies. Analysis of these images will be crucial to confirm the existence of these galaxies and learn more about them. The surprise of these findings highlights how science is constantly evolving, and how we must revise our theories when we have new evidence. Although it is early to rule out the Big Bang theory, this discovery challenges how we understand the early universe and requires a fresh look at our current understanding.